こちらの画面の QR コード、皆様、両者のピッチ対決の後にどちらの、ピッチがより皆さんにとって期待できるか、未来を感じるか、好きかどうかっていうのを、投票していただきます。皆様この QR コードを、携帯で読み込んでいただき、ご準備いただいて、ご参加ください。お願いします。投票は1回しかできませんので、皆さんよく聞いて投票をお願いします。
Ladies and gentlemen, the ultimate pitch showdown has become. Okay, it's coming. Showdown with the Delft and MIT. Okay, for the first is coming to the Henk. Okay, come.
Thank you very much. Good, can I get in?
And from MIT,
Ladies and gentlemen, welcome.
Okay.
Welcome, welcome.
Thank you very much.
Okay. Okay, from now we are doing the short pitch for the two universities. One for the TU Delft and one for the MIT. And so TU Delft is the self-healing concrete and the MIT is the conductive concrete. So please listen and please vote to the which was you're interested. So the pitch time is the 10 minutes. So the first, it's come from the TU Delft. Are you ready?
I'm ready.
Okay, then let's start.
Thank you, ladies and gentlemen. Very welcome to my presentation. But before I start, I would really like to acknowledge Aizawa Company for inviting me to share with you today the technology that we developed at Delft University of Technology, and that is brought to the market by Basilisk and Aizawa Company. Special thanks to Yoshihiro-san for the invitation. But now coming to the technology. What we have developed over the past 15 years is actually a medication for concrete. We make concrete self-healing. And of course you might ask yourself the question, why does concrete need any healing? Why does it need to be improved? Because all of us, we know how to make high quality concrete. That is true. But at the same time, we also need to lower the environmental footprint of regular concrete. We would like to go to a CO2 neutral building process. And for that we need CO2 neutral concrete. There are different ways to achieve that. But one way, very important way, is that we need to become circular. Circular concrete. So we build and we demolish and we rebuild and demolish and rebuild. And we would like to do that at a very low environmental cost. But at the same time, we would also like to do that at a very low economic cost. Because we all want to make business, we all want to make some money. How does self-healing work? How can it help us to make money, but at the same time lower the environmental footprint? One way is to increase the lifetime. So what we have developed, self-healing agent, medication that you can add to the concrete mix. And if you do that, you make high quality concrete. Concrete that has a very, very long lifetime. Because even if it cracks, you will have automatic repair of cracks. Cracks will disappear, and that's because we do not fight with nature. No, we make use of nature. We make use of special bacteria, which are our friends. Not pathogenic, they make us happy and make the concrete perform at a very high level. Because in the medication, probiotics, it's bacteria that can convert the food, the nutrients that is in the medication to limestone. And you all know, as concrete experts, that limestone is a concrete compatible material. It can seal cracks, avoid leakage problems, can also delay the corrosion of the embedded reinforcement. So by doing that, we have multiple benefits. We can increase the lifetime of concrete. We can thereby lower the environmental footprint, because the longer the lifetime of concrete, the less we need to rebuild. So that saves money and also saves the environment. At the same time, we do not need to make a lot of repairs to the concrete, manual repairs. Because if cracking occurs, we typically have to find those cracks, do monitoring, and do the actual repair. And that will all be very costly and also add to the environmental footprint. Now with self-healing, this is not needed anymore. So again, increased lifetime and lowered environmental footprint. Because we have, ladies and gentlemen, we have to continue building, because our society needs more homes. We also need more infrastructure. And therefore we need increased and very high quality. So thanks to the technology that we have developed, this is now possible. And actually, I can tell you one more benefit that we can achieve by applying self-healing concrete. Traditionally, if we make watertight structures, we need to apply, of course, reinforcement. Reinforcement that can add tensile strength to the concrete. But for watertight structures, we also need additional steel reinforcement. And this is because we would like to minimize the formation of cracks in concrete. The more watertight your structure needs to be, the more steel we need to add. And this makes it now sometimes very difficult to cast the concrete for watertight structures, because there's so much steel reinforcement. Now with self-healing, we can solve this problem, because we can reduce the amount of steel that is required in watertight structures. We have made some calculations, and those calculations show that we can easily reduce 30 kilograms of steel per cubic meter of concrete. And if we do that, you might get very small cracks. Cracks of a width of 0.2, 0.25 millimeter. Now you might say, yes, that is an issue, because if we have those cracks in watertight structures, we will have leakage. Well, initially, in the first few days or weeks, you will have some leakage, but then the self-healing kicks in and makes the structure waterproof again. And this is thanks to nature, again, to the formation of limestone. And by doing this, we can not only save 30 kilograms of steel per cubic meter, we can save a lot of money, because steel is expensive, and it is actually more expensive than the costs of the healing agent. So there's a very nice business model. And at the same time, we also know that steel comes with a very high environmental footprint. And so one way to go towards CO2 neutral concrete is lowering the steel by compensating it with a healing agent. So ladies and gentlemen, I think I already have now given you several advantages of using self-healing concrete. It is brought to the market in Japan by Azawa company, and I think you can have seen on the poster that we see here at the back how many batching plants can already provide basilisk self-healing technology to also your structures that you need to build. So ladies and gentlemen, I hope that you are intrigued by our technology and that you are convinced that our technology can also solve your problems. Problems that you might have because you are maybe wondering, how can I make my concrete more CO2 neutral? Well, the solution is relatively easy. You need to add 5 kilos, maybe 7.5 kilos of a healing agent to your concrete mix design. We have already done a lot of different projects. For example, this building also features self-healing in the concrete. So therefore we know that this building will last for a very, very long time. And now you might wonder, how long will it be? It can be hundreds of years. And even if you wonder, do we still need the same building or infrastructure on the same location? If you don't want that, then you can also build demountable. So that means that you can build your concrete structures, prefabricated elements. And those prefabricated elements have as elements a super long lifetime. And if you build in a demountable way, so if you combine Basilisk technology with demountable building, then you can see that you can really achieve CO2 neutral concrete. Because then each element will last for decades, maybe even hundreds of years. So you can demount and then reuse your element for new structure. Or even you could pick up this building, demount it, move somewhere else and put it up there again, without the need to make new cement or even new concrete. So I think, ladies and gentlemen, there are a lot of benefits to the self-healing agent. So combining nature, technology that we have obtained from nature with man-made materials. So then we make a whole new generation of concrete. It's actually living concrete that can help us to also respect the environment. And not only that, as I mentioned, we can actually also save money by extending the lifetime and reducing the amount of steel that we need in structures. So with this, ladies and gentlemen, I would like to finalize, and I hope that the competition here also has a very nice innovation that you might be keen to learn about. And I hope you can vote, and I think we are already both winners, because we have obtained, gotten the advantage, the possibility to present our innovation to you today. So with that, ladies and gentlemen, I would like to thank you for your interest, and if you have any questions, I will be happy to answer them. Thank you.
Okay, thank you, thank you. Okay. 皆さん、自己治癒コンクリートについてのことはよく理解できましたでしょうか。そしたら次は蓄電コンクリートの時間です。Okay, it's time for the conductive concrete. Are you ready? Okay.
I am ready.
Okay, then let's fight.
Well, thank you very much. And first of all, I would like to congratulate Aizawa Concrete and Taishi-san and his father Aizawa-san actually to have built this facility here in Fukushima. It is 12 years ago where all of you of March 11 remember where you were when the accident happened. It was an accident related to the energy produced here in Fukushima. So what I'm going to talk today to you about is an invention how concrete can and hopefully will be the solution for Fukushima to reassume its role as the energy hub of Japan and maybe beyond this year. My name is Franz-Josef Ulm and I'm here with my coach, Admir Magic, who's going to show us some results. So what are we talking about? So first of all, can anybody tell me what are the two materials most consumed on planet Earth? What's the most consumed material consumed on planet Earth? Water. Water. Thank you. Water. What is... Thank you. Thank you. Water. What is the second material most consumed on planet Earth? Beer. Beer. Cement. Cement and concrete. And of course, this is good news for Aizawa Concrete or for anybody who is in the business of concrete, right? But concrete has only one function, which is strength right now, providing shelter for us, for hospitals, infrastructure, etc. But now imagine with me one moment that you can add another function to concrete. Actually, a function which will revolutionize the way how we think about concrete. Concrete as an energy storage solution. Now that sounds almost like science fiction. How can this gray material ever become energy storing? Well, it's not that difficult. You add cement with water, what you all do, you all know that, and then you add a small percentage of carbon black. Carbon black is what? Well, that's the material in your tires which make your tires black. Carbon black. Carbon black is the best material to conduct electrons. Now, the fascinating process happens then here, and I just walk you quickly through it, how that works. Cement is hydrophilic, it loves water, that's why we mix it up with cement in the first place, cement and water to make concrete. But carbon black is hydrophobic, it hates water. But when you bring those two together, out of a sudden you get a volumetric wire, not a straight line linear wire as we have it in our structure, but volumetric wire. And that's the way how you get electron conductivity. You can conduct electrons moving from one side, positive charge, to the negative charge. And what can you do with it? Well, when you have electron charge, electron conductive material, you can heat the concrete, for instance, for de-icing application in the north of Japan. To our friends in Sapporo, that may be hopefully the solution for getting rid of the salt right now used, the millions of dollars or yen spent on de-icing. But there's another property which addresses the key question of the 21st century. How are we going to store energy? Right now, what we have is a battery technology. But as you and I know, batteries are not scalable. Even though Toyota just now revealed one of the best batteries ever. But it's not scalable because we don't have the materials there. But we have cement, water, most consumed on planet Earth, and carbon black at almost the same price as cement. And what then happens actually is if you put a positive charge and a negative charge onto a sample, and my colleague Admir, you're going to see it now on the screen with the camera, when you charge these supercapacitors, the charge is pulled to this volumetric wire and you can store this energy sustainably. Now, what my colleague right now shows, and you should see this now, I believe, on the screen, you're going to see that the light goes on. Now, only charged. Yeah, please. So first of all, we're going to charge it. As you see it, now we're charging basically the cement supercapacitors with a 3 volts, only 3 volts of the material. So a couple of seconds of charging of supercapacitors, which are just 1 millimeter thick or 1.2 millimeter thick, 2 plates separated by a newspaper separator. Everybody can do that. And once it is charged, he takes the conductive off, and now he's going to put just those 2 things in there, and now we're going to see, will the light go on? Yeah, good enough, yes? Yes, and it goes on. Anyway, what you see here actually from this is you can use concrete actually as charge medium. And these are supercapacitors, which are just 1.2 millimeter thick. But now imagine these were actually not 1.2 millimeter thick, but actually 2 wall systems. How much energy you could store? Well, to make an easy calculation for you, for a house, for a typical dwelling, you need, in essence, the foundation to be made out of this material to have enough energy for 1 day of charging, 10 kilowatt hours, 10 kilowatt hours. And then out of a sudden you realize if every building becomes a battery, actually a supercapacitor, we have added a complete new function to concrete. And everybody who will say, oh, concrete is such a dirty material, it produces so much CO2, we have added another value to our society through this material. Like you, I come from a background of engineering, civil engineering. Like you, I've built bridges, I've worked on tunnels, I've worked on these things. Here is a new function where we can gain not only the acceptance of the industry, but actually of the society to embrace concrete in the 21st century. Here coming out of Fukushima, to develop an energy storage solution which everybody can do, available everywhere, and to be done almost in the same way as you do concrete today. And this is the strength of this development. So, energy autarkic homes, energy independent homes could be a first application for shelter. Just think about this, every building you have your own energy in the system. But we can go much further. Well, another application is the self-charging road. Everybody knows how to charge a phone without using a cable, right? That's the same principle, but now imagine that the pavement itself, now electron conducting, and you create an electric field inside the pavement, and you have one, of course, in the car. Then, by electromagnetic induction, you can charge the car automatically. Second application. A third one, inspired actually from what we heard in the previous session about windmills. You know that windmills have today an efficiency which is, if they are perfect, of 60%. Where do we lose the rest 40%? Why do we need to go higher and bigger at it? It's very simple, because we cannot raise the efficiency to a level where we would get all this energy produced by the wind into the system, into the net, or into batteries. And the reason is because wind is not so regular. Turbines do not work so regular. So if we could store this energy actually just in the concrete walls of the superstructure, you can shift the efficiency of a wind system from 60% to 90%. I hope someone from GE Japan is here in the room, let's say, to realize that this is a quantum leap. This is, in essence, if you wanted to increase the power from what we saw today, 1 megawatt to 1.5 megawatt, without changing anything in the design, just by the choice of the material. So, in summary, what I showed you actually here is an idea which emerged during COVID, presented to you here in Fukushima 12 years after the accident, with a vision that that may be a true future for all of us who love the material concrete and want to see it prosper in the 21st century. Thank you very much.
Okay, thank you very much too. Okay. さあ、ここからは投票のお時間に入ります。さて皆様、今聞きましたコンダクティブコンクリート、そしてセルフヒーリングコンクリート、どちらの方に興味を持ったかというところですけども、まず、皆様にお伝えしたいのは、やはりこのような、機会が、設けられるようなこういう場というようなこと、福島 RDM センターというものができたということを、非常に、誇らしく思うとともにですね、皆様、このような素晴らしい、関わりっていうものがいろいろ、できるというようなことが、見えたかと思います。ぜひ皆様も、この施設っていうものがですね、やはり皆さんも同じようにこのつながりというものを持って、使っていただけるような施設になっているということを改めて、考えていただくとともにですね、ぜひ一緒に面白いことを一緒にしていただければと思います。And thank you very much for you guys, Henk and Franz. It was very interesting story, and I'm really thank you to doing this time. It's very important for this facility, and RDM Center is a very important place to connect the people and also like the university or the company. I don't care. I think the connection of the people is very important, and also in this place in Fukushima. So thank you very much for having this time. But it's a battle. So we need to check about the voting. So it is okay. We need more time. もうちょっと時間いりますか?
Did I actually mention that each of you gets 10 kilograms of healing agent for free if you vote for Basel self-healing concrete in your next project? Thank you.
Is they okay?
Okay. Then let's see for the check in the result of the voting. Come on. The winner is MIT Franz-Josef Ulm. Okay. Thank you very much. But also that it says first also that both of the two are the winner also. Yes. It's the very important thing is that we make this kind of the time. This is a very important time. So we want to make this kind of the time in the Fukushima RDM Center from here. And today is the grand opening. And we want to continue this kind of the wonderful time for it. So please continuing joining to the RDM Center. Thank you very much for this time. And thank you for the two guys.
ありがとうございました。
ありがとうございました。この後、このメイン会場では、15時30分午後3時30分より